In this video, we continue our discussion of t-procedures, but now we're talking about two sample problems. Okay, so we're going to be comparing two means to each other. All right, so our motivating example for this set of videos is it's the FIFA Women's World Cup. Woot! The two teams are China and Brazil. Analysts predict China will win. In the last 5 games prior to the World Cup, China had an average final game score of X bar equals 4, and Brazil had an average final game score of X bar equals 3, and we have these standard deviations. The sub C is telling us this is the data that corresponds to China, and the sub B is telling us this is the data that corresponds to Brazil. So is there good evidence that supports the analyst's prediction? So good evidence implies that this is a test of significance. Okay, so eventually we'll get to the point where we can conduct this. All right, and something to note is that comparing two populations is a common statistical practice. Okay, so common statistical practice. So we're at the point now where we're learning skills that can be carried out anywhere. Okay, all right. So our sample, what was our sample? Our sample is the last 5 games prior to the World Cup. It's not a very random sample, but you know, we do what we can. And here's the mean, and here's the standard deviation. All right, so let's talk about the conditions we need to hold for these two sample procedures. So first, both populations, and in our example we have China and Brazil, both populations need to be independent, okay? Which means that we have two simple random samples that come from two distinct populations, and these populations need to be independent. That is, our population here are the game scores for China and Brazil, okay? And does one score influence the other? Well, I think as long as the teams aren't playing against one another in these 5 games, then one team's score doesn't really influence the other. All right, so we then measure the same. And what do we need to measure that's the same? Well, we need to measure the same response variable. Okay, we need to be measuring the same thing in population. It doesn't make sense for us to compare goal scores for one team and yards run for the other. And both populations need to be, you guessed it, normally distributed. Where mu and sigma are unknown. Okay, this is referring back to the simple conditions. So we sort of have a simple condition for each population. It needs to be an SRS, normal distribution, mu and sigma are unknown, but moreover we need the populations to be independent from one another, and we need to be looking at the same variable for both. All right, so if we consider the two populations, we can talk about notation. And so for population 1, we have x1, mu1, and sigma 1. For the second population, we're going to have x2, which is the variable, it should be the same variable, mu2, and sigma 2. All right, so just to give you another example, two populations we might be considering would be 13-year-olds in the US and 13-year-olds in Germany. and we're measuring the time spent playing video games. Right, and then we would compare, so maybe our sample would have to be size 10 here, and we have another sample, so this is N1 and N2, which we'll talk about more later for notation, but these sample sizes do not have to be the same. Okay, why? Because we're comparing means, we're not comparing individuals. So from the population, we have x1, mu1, sigma 1, this is our triple, x2, mu2, sigma 2, this is our triple, but if we're talking about samples, then the information we have would be n1, x bar 1, s1, and n2, x bar 2, s2, okay, where remember that this is our sample size, n1 and n2 are our sample sizes, x bar 1 and x bar 2 are the sample means, and S1 and S2 are the sample standard deviations. All right, and this is the data that we have, and so this is the data we'll compare. All right, and so when we're comparing statistics, we look at the difference between the two. Okay, so we'll be looking at the differences mu1 minus mu2, but since we don't have the mu's, we're inferring onto this difference based off of the difference of x bar 1 minus x bar 2. So let's think about what this distribution looks like now. So we have our sampling distribution, we're looking at the means, mu1 minus mu2, so what we're assuming is that there is no difference. Okay, there's that statement of no difference. So this would be equal to 0 if we're talking about a test of significance, right? And now the values along the x-axis is not going to be x bar 1, x bar 2, etc. What it's going to be is the sample mean from the first population minus the sample mean from the second population. And this is from our first sample. Okay, and then the other data is x bar 1, so x bar from our first sample minus x bar from our second sample. Sorry, x bar from our first population, x bar from our second population, this is the second sample that we drew from each two, so that this is the difference. And you would do this over and over again and build this normal distribution up, or normal-ish. I'm drawing normal, but there's no reason why it has to be normal. So just to relate this to a real-life context, let's say we want to compare whether college freshmen at Simon's Rock are smarter than those at Bard Annandale, then our null hypothesis is going to be that mu1, so whichever population we designate as the first population, minus mu2, whichever population we designate as the second, so mu1 minus mu2, is equal to 0, so that we're saying that there's no difference, all right? And then for our alternative, let's say that there is some difference. Okay, so either we're saying that Simon's Rock freshmen are smarter, or we're saying that they're not. It depends on who's making the claim, I guess. Okay, so either there's a positive difference or a negative difference. All right, and here, population 1 could be Simon's Rock college freshmen, population 2 can be Bard Annandale's college freshmen. And so the question you should be asking, and I won't answer it here, is, does order matter? And as we're talking about our procedures, keep asking this question, does order matter? Does it matter which one's population 1, which one's population 2? Alright, so let's talk a little bit more about these T procedures, these two sample T procedures. So we're looking at the observed difference. So that's x bar 1 minus x bar 2. And what do we know? Well, we know that it has the standard deviation is equal to sigma 1 squared over n1 plus sigma 2 squared over n2. Where these formula come from requires a lot more theory than we're going to discuss in this class, because it comes from calculus-based statistics. But to give you some intuition, recall that a single sampling distribution has the standard deviation sigma over square root n. Okay? If we square this, then we get sigma squared over n. Right? So now if we have two different sampling distributions, sigma squared and sigma 2 squared over n2, what we're doing here is we're combining them. And then we're taking the standard deviation. So we're sort of working backwards in that way, but we're combining the two standard deviations for the two different sampling distributions. All right? And the standard error is just the standard deviation without sigma. Okay, so if we change this to s1 squared, n1, because we don't have sigma, so we can't use it. Then this is our standard error, and we call that SE. But just like all our other methods, we're going to standardize x bar 1 minus x bar 2, and we get a new t-statistic. Yet another t-statistic. T is equal to, and so here is what it was before. And so we're translating this into what we have now. X bar is x bar 1 minus x bar 2. Right, this is our sample difference. Minus, what is our null difference? Well, our null is a statement of no difference, so that just means it's 0, which is mu1 minus mu2 is equal to 0. This is our null statement for all two-sample t procedures. Divided by, and well, we know that this is different now. We're just going to plug in our new fancy s1 squared over n1 plus s2 squared over n2. So this is our new t-statistic. And this two-sample t-statistic has approximately a t-distribution. It's not an exact t-distribution, which is the difference between the two-sample t-statistic and the one-sample t-statistic. So it has an approximate t-distribution, and it never has an exact t-distribution, even if the populations are both normal. Okay, that's something to keep in mind. This is what makes it different. All right, so now that we have some facts under our belt, let's just talk about how that modifies our formula. Okay, so remember before we had x bar plus minus t star s over square root of n. So we're replacing our standard deviation with our new standard deviation. And we're replacing our statistic with our new statistic. And that's the only thing that changes. Well, I lied. Now we have this new formula for degrees of freedom. So we want to choose the smallest degree of freedom because we would like to be more conservative. More conservative. All right, and when we're talking about tests of significance, this is, I think we just went over that actually. This is our new test of significance, t-statistic, and again we choose our p-value based off of the minimal degree of freedom. Okay. So let's go ahead and just complete the motivating example so that this is a fairly comprehensive video. Alright, so step 1, state the null hypothesis. Well, we know our null for two-sample t procedures is always going to be that there is no difference between the two populations, so the average goal of China is equal to the average goals made by Brazil. And our alternative is that mu c is greater than mu b, because the analysts claim that China is going to win. Alright, so now we want to calculate our t-statistic, and so that is x bar c minus x bar b, which is 4 minus 3, and then we plug in s1 squared, is 1, over n1 plus s2 squared over n2, and then if you plug this into a calculator, you get that this is equal to 2.4113. We know that the degrees of freedom is equal to 4, and so if we go to table C, we go to the row of degrees of freedom 4, which we already have highlighted. That's nice. And we're looking for 2.4113, so 2.4113 lives here. So we follow that down to our one-sided p row, and we see that our p is less than 0.05. So p is less than 0.05, which says we reject H0 in favor of HA, implies that analysts' prediction is likely to be correct, and our evidence is statistically significant at level alpha equals 0.05. So please note that the two-sample t procedures, they have their own rules of robustness, and you should read it. I'm not going to cover it in this video because this video is already super long, but you should read it and bring questions to class, okay?
My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. We live in a world of technology. They're collecting information on your humanity. Social networks, gaming, and in-home software.
Hello, Alexa.
Statistics helps us be more aware. Haters gonna hate my spicy lyrics. Why you gotta be so mean? Pulling me towards your extreme moods, but the median never fails to center me. 50 to my left, 50 to my right. Got these correlation and regression tools, forget them fools. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. The mean of the means is the mean. The mean of the means is the mean. The mean of the means is the mean is the mean of the means is the mean is the mean. Be careful not to fall in love. Statistical seduction from above. Your shape so beautifully symmetric to the eye with a single peak so high. I hypothesize and can testify that your p-value is the smallest I've seen. Mix that with a large power and I reach ecstasy. Your residuals defy the rest. A small scale randomized pattern tells me you are the best fit. My name is Llama, and I'm here to teach you stats, skilling you up with the cold hard facts. My confidence is so high, 95%. My margin of error so nil, 110. Can you feel me? Can you feel feel me? I estimate your population parameter based on only one sampling. Oh, haven't the frequentists told you about me? We live in a world of data, attempting to understand life by statistical strife. The implicit bias of cops, success rate of them jocks, medical advances, and AI romances. Statistics.